Hello students, this is Dr. Siva Nagaju from IARE. Today we are going to discuss about two modulation techniques. One is quadrature phase shift keying and another is differential phase shift keying. This quadrature phase shift keying in simple form we can written as QPSK. Quadrature phase shifting key, and another is a DPSK, differential phase shift key. So, what is the differences between ordinary phase shift key and for the new QPSK and DPSK? For digital modulation techniques were divided into two types. One is binary and IARE. In binary, we are used only one bit we can send data, either 1 or 0, that is. Whereas in IARE, we can send more than one bit, that is 2 bits data. That is we can call as IARE technique. Whereas the second version, there is coherent and non-coherent versions. We can take another way and differentiate these digital model techniques either in coherent or in non-coherent. So actually coherent and non-coherent terms is regularly used at receiver point. So what you are doing at receiver, we are going to detect the original signal, original message signal. So in what way we are going to identify or retrieving the message signal? That is, you can use by phase difference or without phase difference. So with phase difference, we can call it as coherent. We are not using any phase value. We are not using any phase value for identifying or retrieving the message signal. That is called as non-coherent version. So why I'm talking all this means the DPSK is the differential phase shift keying can be viewed as a non-coherent version of PSK. So that's why here a little bit introduction about what is coherent and non-coherent. Okay. Coming to the topic. So first we are going to discuss with the course outcome. So actually these two topics are come in module 4 under CO4. Course outcome 4. So what the course outcome for? Analyze the digital passband communication schemes using modulation and demodulation process. So already we know that this passband and baseband difference. Baseband means the original message signal. This original message signal is not suitable for radio link. So that's why we are going to convert or transfer this baseband signal into a passband form by modulating. Okay. So in that modulation, we are having binary and IARE. So these ASK, PSK, FSK, these can be called as binary modulation techniques. Whereas the present one is QPSK is a simple form of IARE. Okay. So what is this quadrature phase shift key? So an important goal of digital communication is the efficient utilization of channel bandwidth. So why here this term is used, efficient utilization. Whereas in the previous techniques, whatever we discussed, which are binary form. That means they can send only one bit at a time. That is either 1 or 0. So this is a wastage of this channel bandwidth. So we have an idea. We can send 2 bits at a time. Then we can utilize the channel more efficiently. So that's why this quadrature phase shift keying has come to this picture. So in this QPSK, we can send 2 bits at a time. That is, here we can send 2 bits. How? This is related with our binary. That is, m is equal to 2 power n. Okay. So how many bits we are sending? 2 bits. Then it is called as m array. If we send only 1 bit, n equal to 1, that is we can call as binary. If m is more than 1, n value, here n value is more than 1, we can call as m array. So 2 bits at a time we can send by using QPSK. So that's why these 2 bits can be called as D bits. So a group of 2 bits is often called as a D bits. So 4 D bits are possible. So each symbol carries same energy. So whereas in binary we are called as energy per bit. Why? You can send either 1 or 0. So what is that energy? That is EB, energy per bit. But here we are send these 2 bits as a symbol. So 2 bits we can send as a symbol. So here we consider symbol energies. Okay. So there is a difference between this binary and MRS. So now in QPSK, as with BPSK, information carried by the transmit signal is contained in the phase of sinusoidal carrier. So in particular, the phase of the sinusoidal carry takes on one of 4 equally spaced values, such as pi by 4, 3 pi by 4, 5 pi by 4, and 7 pi by 4. That means here this carrier can take 4 possible. Where you go for the BPSK, it having only 2 phases. That is 0 and 180 degrees. 0 degrees and 180 degrees. So there is a difference between 1 and 0. So that is a phase can show in the difference between 1 and 0. Whereas in QPSK, we uses these 4 possible phase values for the transmit of the symbol. So SI of t is the modulated QPSK signal, which is equal to square root of 2e by t cos of cos 2 pi, cos of 2 pi fct plus 2i minus 1 into pi by 4. In the region of 0 to t, capital T is the symbol duration. Here you can see E is the symbol energy and T is the symbol duration. Where I is from, we can change the I value. So the phase values is going to change. Why? Because this is cos of A plus B. We can rearrange this cos function as cos of A plus B equal to cos A cos B minus sin A sin B. In that form, we can see the modulated signal, which contains the 4 possible values, depends on the I value. If I value changes, so here we also the value has changed. For example, I equal to 1. For I equal to 1, that is 2 minus 1, that is pi by 4. Simply, for I equal to 1, we got pi by 4. For I equal to 2, that is 2 into 2, we got 4 minus 1, that is 3 pi by 4. My I value is 3. Then 2 is multiplied with 3, we got 6 minus 1, that is 5 pi by 4. But again I equal to 4, so the value is 7 pi by 4. So my I value changes from 1, 2, 3, 4. Why? Here I taken 4 possibly phase values. So 4 phase values. Okay. So here E is the energy per symbol, T is the symbol, duration. So already we told that is sent as a D bit, that is 2 bits. So the symbol duration is also equal to 2 into TB, where TB is the bit duration. Okay. So the set of phase values to represent the gray encoded set of D bits. So these 4 phase values can take these 4 gray coded D bits. So for the pi by 4 it is 1 0, for 3 pi by 4 it is 0 0, for 5 pi by 4 it is 0 1, and 7 pi by 4 as 1 1. So there is a 4 phase values can represent this 4 gray encoded D bits. So here you can see. So the first D bit is 1 0. So here the phase of QPSK is pi by 4. And the coordinates of signal is root of E by 2 minus root of E by 2, where I value is 1. Okay. So that is, we can see that function Si of t is equal to square root of 2E by t cos of. So in that cos of, we are having cos of A plus B formula. So we can divide into cos A, cos B minus sin A, sin B. So after substitution of I value, then we got this square root of E by 2 and minus E by 2, minus root of E by 2. And for I value equal to 2, the D bit is 0 0. And the phase of this QPSK is 3 pi by 4. And the coordinates of the signal points values are minus square root of E by 2 and again minus square root of E by 2. That is for I equal to 2. Where again I equal to 3. For I equal to 3, my QPSK phase value is 5 pi by 4 and the D bit is 0 1. You can see. And here the coordinates values are minus root E by 2 and plus root E by 2. That is taken from that the first modulated of QPSK function or equation, that is S I of t, that is equal to square root of 2E by t cos of, here we are taken that is in the form of A plus B is there. So B is the phase value in that term. So we are dividing this one and substituting I values, you get these coordinates of signal points. And again, where I equal to 4, my D bits are 1 1 and the phase value is 7 pi by 4. Okay. So this is for QPSK coordinates, signal points. Okay. So here the equivalent of that function. So it is square root of 2E by t cos of 2I minus 1 pi by 4 and cos 2 pi FCT. That is what we have written for the SI of t is equal to square root of 2E by t cos of 2 pi FCT plus 2I minus 1 into pi by 4. So this is the first equation for representation of this modulated QPSK signal. So here by cos of A plus B formula is going to apply, and here we written as cos A cos B minus sin A sin B, and substituting I values we get that previous table you can see. So that values are kept. And now QPSK transmitter. So this is my QPSK transmitter. So here the input is the binary data sequence which is coming, that is applied to the NRZ encoder. That means here they are coming as ones and zeros. Why? The binary data means 1 0 1 like that. So this is the sequence what is coming to the this NRZ encoder. Why? Because for the line coding, we know that NRZ, RZ, BRZ, Manchester, different type of line formats are there. So that line format we can use any one coding technique, that is here I taken as NRZ, non-return to 0. So that means the 0 value is not returned. So either positive or negative value in the NRZ. So here I am going to assign for 1 as root AB and 0 as minus root AB. And this is going to apply to the demultiplexer. The demultiplexer distributes those values for the upper channel and the lower channel. And again the upper channel is multiplexer with this pi 1 of t. What is the pi 1 of t? There is a basis function. Already we discussed it in the PSK, FSK. So here we represent this SI of t by using two basis functions. That is one is pi 1 of t and another is the pi 2 of t. So this pi 1 of t is equipped with the upper channel and pi 2 of t is equipped with the lower channel. And again these two outputs is going to added by using a summer. Then we are producing the required QPSK signal. Okay, this is my required QPSK. Why? It having 2 bits. So from this 1 bit is coming and another 1 bit is coming. So we produce like 1 1 or 1 0 or 0 1 or 0 0. So these 2 bits are produced at the output of this transmitter. Okay, so again you can see the this block diagram description. So the incoming binary data sequence is first transformed into a polar form of NRZ level encoder. Thus, symbols 1 and 0 represented by plus root AB and minus root AB respectively. Why? This is NRZ, no 0 values there. So, for 1, I am assigning plus root AB. For 0, I am assigning minus root EB. So, this binary wave is next divided by means of demux into 2 separate binary waves consisting the odd and even number input bits. Okay, and these 2 binary waves are denoted as A1 of t and A2 of t. So the 2 binary waves A1 of t and A2 of t are used to model the pair of orthonormal basis functions. So in that picture you can see orthonormal basis function is pi 1 of t and pi 2 of t. So the result is a pair of binary PSK which may be connected independently to the orthogonality of pi 1 of t and pi 2 of t. So simply we can say finally when you are going to add in 2 PSK signal, you can require the desired PSK signal. Why? Here in that transmitter we having upper channel is coming and again the lower channel also coming. So here the summation is taken. Okay, so the upper channel is equipped with pi 1 of t and the lower channel is equipped with pi 2 of t, and here this is A1 of t and this is A2 of t, the second part. Okay, so we can consider this the upper as one PSK signal and the lower as another PSK. So here I am going to adding 2 P signals, then I am going to produce the required QPSK signal, that is quadrature phase shift key. Okay, and another that is a receiver, QPSK receiver. So here we are going to take the received signal is nothing but our QPSK. So here also we are using 2 basis functions, orthonormal basis functions. So already we discussed orthonormal basis functions are defined by the Gram-Schmidt orthogonalization procedure. From that procedure we are going to operate this one. Okay, so the received signal is nothing but QPSK. So the QP signal must contain this pi 1 of t and pi 2 of t. For two basis functions are there. Why? Because in previously we discussed how the QPSK is generated. Just by adding two PSK signals, then you get QPSK. So one PSK contains one basis function. So here I am adding two basis functions. So that is a two PSK signal contains two symbols. So we don't know either upper one is 0 or lower one is 0. Okay. So here we are sending this QPSK signal to the upper channel, again is the lower channel. So here the pi 1 of t, which matches with the pi 1 of t in the QPSK signal, then it produces the output from the integrator, and it is sent to the decision making device. So the decision making device contains a threshold level, that is nothing but the 0 we can take, that is upper channel or in phase channel, and the lower channel is called as quadrature. So the lower channel is equipped with pi 2 of t and also same as the integrator. So the output is again fed to the decision making device. So here it produces either 1 or 0. Why here it may be 1 1? Same 1 1 is going to apply for this one. Okay. So the decision is taken. If it reaches the threshold, so it takes 1. Not exceeds, taken as 0. So finally we are going to multiplexer. So and finally we are producing the estimate of transmit binary sequence. So that is the QPSK receiver. Okay. So here the description about this QPSK receiver. So the QPSK receiver consists of a pair of correlators with common input and supplied with the locally generated pair of coherent reference signals pi 1 of t and pi 2 of t. The correlator outputs x1 and x2 are each compared with the threshold values of 0 volts. If x1 is greater than 0, decision make is in favor of symbol 1 for the upper channel. If decision not if threshold is not exceeded, then decision makes in favor of symbol 0. Why? Because this is binary, so either 1 or 0. For the again second part, similarly, if x2 is greater than 0, decision is made in favor of symbol 1 for the lower or quadrature channel, and similarly for the second output also taken. Okay, so finally you're going to add these two binary sequence in phase and quadrature and combined by a multiplexer to produce the original binary sequence at the transmitter input with the minimum probability of error. Why? Here we are going for the coherent version. So in coherent we have minimum probability of errors for coherent. For non-coherent, the probability of errors are more. Okay, so there is QPSK. So next applications where this QPSK is used. Nowadays QPSK are used in a number of ways. So one we will take the simple sum of. QPSK is used for satellite transmission for MBG2, video cable modems, video conferencing, cellular phone systems, and other forms of digital communications over an RF carrier. So that is the applications of QPSK. And another one is DPSK. This is nothing but differential phase shift key. Differential. So this DPSK may be viewed as the non-coherent version of PSK. Why? Here, non-coherent means we're not taking any phase or avoiding the requirement of phase signal. So here, without phase means there is no sense in PSK. So that's why DPSK may be viewed as the non-coherent version of PSK. Why non-coherent version of FSK is available? But this non-coherent of PSK is not directly available. But DPSK may be used as the non-coherention of PSK. So DPSK eliminates the need for coherent reference signal at the receiver by combining two basic operations at the transmitter. So what are the two operations? Differential encoding of the input binary wave and phase shift keying. That means first it is going to encoding, differential encoding of the input binary wave. So this differential encoding is very, very important in exam point of view also. So the problems will come on this differential encoding. And in this session, we are going to solve two simple problems. How to solve taking binary sequence and how to encode this differentially by one as a reference bit for one problem and another problem 0 as the reference bit. Okay, let's see in lots of session. So in effect, to send symbol 0, we phase advance the current signal waveform by 180 degrees, and to send symbol 1, we leave the phase of the current signal waveform unchanged. So that is nothing but PSK. What is the PSK? PSK is providing 180 degrees phase shift for symbol 0, and for symbol 1 there is no phase shift. So that's why this is PSK can be called as antipodal signals. That is, antipodal means these two lying in the same but in opposite sense. Okay, so that is one as root AB, another is 0. So that is for PSK. This is PSK. Okay, so PSK called antipodal. The differential encoding process at the transmitter input starts with an arbitrary first bit, serving merely as a reference. Let DK denote the differential encode sequence with this added reference bit. To generate this sequence, the transmitter performs the following two operations. So what are the two operations? If the incoming binary symbol BK is 1, then the symbol DK is unchanged with respect to the previous symbol DK minus 1. So here DK minus 1, that is a D suffix 1, actually DK minus 1. So that is a previous symbol for DK. Okay, and again if the incoming signal BK is 0, then the previous symbol DK is changed with respect to the previous symbol DK minus 1. Okay. The differential encoded sequence DK thus generated is used to phase shift a sinusoidal carrier wave with the phase angle 0 degrees and pi radians. 0 degrees and pi radians, representing symbol 1 and 0 respectively. So for symbol 1 is coming, there is no phase change. For symbol 0 is coming, there is a phase change of 180 degrees. Okay. So these are the transmitter receiver for a DPSK. So here you can see the input binary sequence is coming, that we can call as BK. By using the BK, here this DK is generated. That is the differentially encoded sequence. So how this differentially encoded sequence is generated? By using previous DK, previous bit of this differential encoded sequence, and here we are using a logic network. Okay, and then it is applied to the amplitude level shifter, then it is product model. So this half part is differential encoding and the remaining part is ordinary PSK. Already we say that at the starting of DPSK, two operations are done at the transmitter. What are the two operations? One is differentially encoded. So this is the first part, differentially encoded, and then after PSK. So this is normal PSK. So this is differential encoded and this is ordinary PSK. So the result is DPSK signal is produced. Here just amplitude level shifter is used. For symbol 1, it is used to represent as root EB. For symbol 0, there is this. So that is here we can take. Okay. And the below one is receiver. So the receiver is also contain a correlator. So before the correlator, we are passing this receive signal to the band pass filter. So the band pass filter, which allows that certain band. So what is given at the transmitter, such band is going to allow. The remaining bands are going to attenuate. So after passing the signal from the band pass filter, passes through the correlator. So the correlator is nothing but the product modulator and integrator, been called as correlator. So the correlator produces an output of L. So this L is fed to the decision making device. So the decision making device generally having a threshold level. So the threshold level is taken as 0. So here you can shows choose 1 if L greater than 0, or choose 0 if L less than 0. So this 0 is a threshold. So if the L value exceeds the threshold, then it chooses 1. If L value does not exceed or less than threshold value, simply choose 0. But some people having doubt. If it is exact 0, what to do? So that is makes that is given to the decision making device decision. So it takes either 1 or 0. So that is the error will going to generate. So but such a probability of errors are less when you go for the coherent version. So that's why here such case is not arising regularly, but sometimes it may be happen. Okay. So now we are taking one problem, that is problem 1 as a reference bit. So 1 as a reference bit. So first what I required decay. That is the binary sequence. So here I taken binary sequence 1 0 1 1 0 0 1. So this is a given binary sequence. From this binary sequence I am going to produce the decay minus 1. So what is decay minus 1? The previous bit of the differentially encoded sequence. Okay, so how to generate? So here what is given? 1 as the reference bit. So first I take a 1. This is the reference bit. From this reference bit, I am going to start to produce decay minus 1. So there is a simple procedure how to produce this decay minus 1 or previous encoded sequence, differential encode sequence. So there is a OR operation. There is OR operation, the logical OR operation in between BK bits. So here 1 0. What is the OR operation? That is 1 0 1. Again 0 1 1 1 1. Again 1 1 0 1 0 0 0 0 0 0 0 1. Again 1. So that is my decay minus 1. How to produce? Just the OR operation in between BK, in between the binary sequence. Okay. Now here I am going to the phase of this decay minus 1. Here I am giving a phase. So what here for already told for 0 there is no phase change. So for 1s there is no phase change. For 0 there is represented as pi. So again 0 here also. Okay. Then I am going to produce this decay. What is decay? Decay is the differential encode sequence, where decay minus 1 is the previous bit of this decay. Okay. So here for producing of decay, there is a logical operation is there. Already in the block diagram is shown logical operator. Okay. Okay. So what the logical operation is? Bk modulo to sum of dk minus 1 x. So here XNOR operation simply. Why? Because this we can call a modulo to sum. Modulo to sum is also equivalent to the XOR. Okay. So the complement of this XOR. So simply it is XNOR. So here we are going to here also the reference bit is 1. So for reference bit 1 we take it. Okay. So we are going to operate in between this BK and DK minus 1. BK is the input sequence. DK minus 1 is the what you generate by applying a simple OR operation between BK. Okay. So now the DK is the complement of this BK XOR to the DK minus 1. So here we go to operate in between these two. So 1 1 is 0 for XOR, but the complement it is 1. Again 0 1 is 1 for XOR, but complement is 0, and 1 1 is also 0 for XOR, but complement of XOR is 1. So similarly 1 and 0 1 is 0, 0 0 1. While 0 0 is 0, but the complement is there. So 1. Again 0 0 1. So 1 1 also produces 1. Why? 1 1 is 0 for XOR, but complement is 1. Okay. So this is my DK. So DK is the differentially encoded sequence. So this is over at the transmitter level. But here phase comparison is also taken the receiver. So here the phase of DK I am taking. So for 1 again similarly there is no phase change. For 0 pi again 1 0, and this one also 0, and 0 pi 0 0. So this is my phase values of decay. Okay. Now the phase comparison between dk minus 1 and dk. So this is the phase value. This is the phase value. Okay. Phase of dk minus 1, phase of dk. So here we are going to compare these two. These two is going to compare. So there is any change for 0 0? No. So there is no phase change, means here it produces as 1. So again 0 to pi. So there is a phase change. So it is 0. And this one again same phase, no change. Again this one there is no phase change, 1. 0 pi. So this is a phase change. And pi to 0. So this is also phase change, 0. And this is also a phase change, 0. And 0 0. So there is no phase change, 1. So what you get? This is similar to the decay. Okay. So this problem taken as 1 as reference page. Okay. For the next we take again problem 0 as the reference page. Okay. So this is again I required BK, that is input binary sequence. So same sequence I am considering. So 1 0 1 1 0 1. So what we taken as for 1 as reference bit, but here 0 as the reference bit. So this is dk minus 1. So for 0 as reference bit, so that's why starting bit is 0. So now how to produce dk minus 1 for 0 as a reference bit. So here complement of R, simply complement of R. Whereas previously we taken as a OR operation in between BK, but here complement of R. So 1 0, what you got? You apply complement of R. So that do not forget. So 1 0, generally 1, but complement is 0. So again 0 1 is 0, 1 1 also 0, 0 1, sorry, 0 1, this one 1 1 and 1 0. So this also 0. So 0 0, it takes 1, 0 0 1 and 0 1 also it takes 0. Why? So this is complement of R, logical R. Okay. So here also we take the same phase values. Why it is useful at the receiver for comparison. So phase of decay minus 1. So for 0 are taken as paradians. For 1 there is no phase change and this is also high. Okay. So then after we go for the encoded sequence. That is differential encoded sequence decay, but here 0 as a reference bit. So 0 as the reference bit. So for the first bit 0 as taken as. Now what is the logical operation? Okay, so here we are going to produce this decay that is similar to that what we discussed in the problem. One as reference bit. So from that we are going to generate this decay. So what we taken? It is a complement of modulo to some adder. So here by using that one we generated 0 1 double 0 1 again this triple 0. So similar to the one reference bit. So here also we taken the phase of decay. So for 0 again pi and for 1 no change and again 0 pi and this pi 0 pi 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 again. Okay, so here the recovering bits are recovering bits. So you are going to compare the phase values of decay minus 1 to decay. So there is no phase change, that is 1. If phase change taken as 0, 1, there is no phase change 1. So there is phase change 0. So here also the phase change. So here also the phase change. So there is no phase change. So that is a problem. So what we solve here. Okay. So coming to the references. So here we are taken the kind of this information is taken from Community Systems by Simon Hacking, 3rd edition. And again another book is content of information is taken from Digital Communications from Simon Hacking. So both are from Simon Hacking. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.